Hey everyone, welcome back to AP Pre-Calc. This is lesson 3.2. Let's get right into it. All right, so here's the bell ringer for today. Pause the video if you haven't done this already, because I am about to go over the answer. So if we know the period of a function is 7, and then we are given that f of 7 is equal to 7 here, and then f of 3 is equal to 9, we want to know what is f of 24. And one thing that we know about periodic functions is that if you take 3, right, that x value of 3, and you add or subtract any multiple of the period, right? So like let's say we add one period, which is 7, to get 10, f of 10 is also going to be 9. Likewise with f of 17 and so on and so forth. Same thing with 7, right? If we go one period to the right at 14, that's going to have a y value of 7. It's going to be the same y value when it's exactly 1 or 2 or 3 or -1 periods apart. And so to find f of 24, all we need to do is subtract periods of 7 to maybe get one of the 2 points that we were given. So let's say we subtract a period. This is going to be equal to f of 17. That doesn't match anything, so let's subtract another period to get f of 10, which is also f of 3, which we know is 9. So that means f of 24 equals 9, and that is going to be our answer there. All right, so now let's go over a quick few definitions for today's lesson that you will need to know. All right, so the first definition we have is standard position. And basically an angle in standard position is going to be mostly the angles that we're going to look at here. And so all is the center point of the angle, right? The vertex, which is right here of an angle, is going to be at the origin at 0, 0. That will always be the case. One of the two rays, so this right here is the ray, and then the vertex of an angle. One ray will lie always on the positive x-axis, so right there. And then the other ray is dependent on how large the angle is, right? So in this example, it's like this. That's standard position, but it could also be, if I'd use green now, for example, you could have an angle in standard position that looks like that. You could also have, to draw just one more, an angle in standard position that looks like that. So all three of those are angles in standard position. The second definition is just terminal ray, and that's going to be the second ray of the angle in standard position that's not on the positive x-axis. So in this case, this right here is the terminal ray, that ray there. The other ray that lies on the positive x-axis is going to be called the initial ray. So here now we have all three parts of a standard position angle, which is if we have our xy axis, this right here is the vertex. This right here that I'm drawing now is going to be the initial ray. And then this right here that I'm drawing in blue is going to be the terminal ray. And that is a standard position angle. And then finally, the definition that we will talk about last is displacement, and that is the direct distance from one thing to the other. It's the shortest distance possible, and so here, this is an example of distance versus displacement. Is distance may be a long path, but displacement is just the shortest possible path between two objects there. All right, now let's talk about positive and negative angles. And so positive angles, pretty simply put, are just going to be in the counterclockwise direction. I know it may seem a little bit weird. Negative angles are going to be in the clockwise direction. And so all positive and negative does is just indicate the direction of rotation from the positive x-axis. So for example, this angle right here, if we had to estimate, I would say that this is around positive 45 degrees. You don't always have to add the plus. And then this angle right here, if I had to estimate it, because it is clockwise, I would say that this is around negative 45 degrees as like an angle measure there. All right, so now that we got all the definitions out of the way, let's label the circle to the right. And so let's start easy. O is going to be the origin, which is the point 0, comma 0 there. X here, if we take a look at that dotted line, what is that dotted line exactly? That is the distance from P to the y-axis. And so we are going to call this the horizontal displacement of P from the y-axis, because that is what x is. If we take a look at y, what is y? Y is going to be, I'll do it in green here, this distance from P, and not from the y-axis this time, but from the x-axis. So y should be the vertical displacement of P from the x-axis. What is r? R is just going to be our radius in this case, or it's the distance between the origin and point P. So r is radius or distance between origin and point P. And then theta here is, from our definition, just an angle in standard position. And then P right here is, if we kind of erase all this work, oops, here, what is P exactly? P is going to be where this terminal ray intersects this circle. And that intersection point is point P. So point P, by definition, is going to be where the terminal ray intersects the circle. And that should be our definitions there. All right, so now an important thing for this lesson is making sure you remember SOHCAHTOA. That's kind of why I had you do the trig review. And so here for SOHCAHTOA, all we need to do is remember SOHCAHTOA, which means sine is going to be, of this angle, is going to be the opposite side, which is just the side across from it, over the hypotenuse, which is the side that is always opposite the right angle, so O over H. Cosine is going to be adjacent over hypotenuse. And then tangent, or TOA, is going to be opposite over adjacent. So making sure that you have those ratios kind of memorized is really going to be helpful for today's lesson. All right, so now what is sine, cosine, and tangent in terms of more advanced definitions than just SOHCAHTOA? Right, so let's say we have this angle in standard position and the circle that we just labeled, where the terminal ray right here intersects the circle at point P. What is sine, cosine, and tangent of this angle right here? Sine, if we think of this as a right triangle, right, with this being R, this being Y, and then this being X. So let me almost like redraw this triangle kind of separate from it so it makes a little bit more sense. Where we have this triangle here, where this is our theta, this is our radius, this is our y, and then we're going to say this is the same value as x right there, so this is x. Sine is going to be the ratio, by definition, of the vertical displacement, which is y, of P from the x-axis to the distance between the origin and point P. That's just a fancy way of saying r. And so sine is the ratio of y over r, or in this case, for theta, opposite over hypotenuse. So it's really just taking these definitions that we've learned in geometry and applying them to this circle here where it's a little bit more advanced. Cosine, very similar. A lot of people want to just say cosine is adjacent over hypotenuse. That is correct, right? In this case, it would be adjacent would be x over hypotenuse, which is r. But the formal definition is the ratio of x, which is the horizontal displacement of p from the y-axis, which is right here. And then r is the distance between the origin and point P. So that's x over r. Tangent, likewise, is going to be the slope of the terminal ray. Or let's take a look at the ratio first. The ratio of the vertical displacement of P to the horizontal displacement of P. So that's going to be the vertical is going to be y, and then the horizontal will be x. So it's just going to be y over x. However, if we think about this, right, what is the slope of this line? It's going to be rise over run is slope. And rise, in this case, is our y value, and run is our x. So rise over run is our slope, but what is it also? It's also tangent. We also can get tangent by doing sine over cosine. If we take a look here, doing sine over cosine is equal to y over r divided by x over r. Turning this division into a multiplication, you keep, change, flip, so times r over x. The r's will cancel out, and you should be left with y over x, which is what we have there. So we can also say tangent is sine over cosine. That's going to be very important as well when we talk about tangent in a few lessons. All right, so example number 1. The figure shows a circle centered at the origin with an angle theta in standard position. The terminal ray intersects a circle at point P. The coordinates of P are x, comma, y. What of the following is true about cosine? And so here, cosine, if we draw out this triangle, right? Let's do that. We don't know what x and y are, but that's okay. We don't need to know because everything is in terms of x, y, or they have 3, which here you're going to get your radius, this distance right here, from this, because this distance is the same as this distance right here, because all radii of the circle are the same. So this is going to be 3. This is our x value, and then our y value there. So that's how I would label that triangle to start with. Once we have this, what is cosine? So cosine theta, using the definitions that you've done before, is just adjacent over hypotenuse. But then in terms of x, y, and 3, adjacent is x over hypotenuse is 3. So we're looking for cosine is x over 3. So A would be the correct answer there. All right, example number 2. The figure shows a circle, same setup. The coordinates are x, comma, y. The radius is also 3. Which of the following is true about tangent? And so you'll see a question like this. Tangent is going to be, if we draw that triangle out again, here theta, x, y, and r, which we know is equal to 3. Tangent is going to be opposite over adjacent, which in this case is y over x. And that will always be tangent for here. And so this should be tangent is y over x. So C is the correct answer there. And then with that, we can eliminate A, B, and D without even looking at the definitions. But the definitions make sense though, right? It's the ratio of the vertical displacement, which is y, to the horizontal displacement, which is x. So y over x there. Right, example number 3. Which of the following is true about sine of theta? And it's the exact same setup as before. Taking a look at this triangle, this is theta. We get x, y, and 3. So sine is opposite over hypotenuse, which is going to be, in this case, opposite is y over hypotenuse is 3. So we're looking for sine as y over 3. So B should be our correct answer there. All right, so one little math hack is if you want to find sine, cosine, or tangent a lot faster than just memorizing these ratios, simply just draw a triangle using one side of the triangle as the x-axis, either positive or negative. and then use SOHCAHTOA. And so this is what we call a reference triangle, is the triangle that we're gonna use SOHCAHTOA with. So let's say we've been working simply with angles in the first quadrant so far, which is great, but what happens if we have an angle in standard position, let's say like that, right? How do we find sine, cosine, and tangent of that? Well, what we're gonna do is we're going to draw this triangle right here, where one side is with the x-axis, one side is going to be the radius, and then the other side is the side that forms that right angle. And then we are just going to do SOHCAHTOA on that triangle, where if this is, let's say, negative 3 comma 4, right? Then this would be negative 3, this would be positive 4, and then positive 5. So those would be the numbers that we would use for our side lengths. So this is the first time where you may have negative side lengths, which is going to be okay because we're working in all four quadrants. Let's do example 4 real quick. Draw the reference triangle. So here, it's either going to be one of these four triangles are going to be your reference triangle. And it's going to really just depend on what quadrant you're in. So here, my reference triangle is going to be like that. That should be my answer to example number 4. All right, and then the next step is like label the sides of your triangle. So this is a weird part because, like I said, you could have negative side lengths. For example, let's say we have the coordinate negative 3 and then negative 4. And we know the radius will always be positive. So in this case, the radius is going to be 5. That distance will never be negative, no matter what. Then we want to use SOHCAHTOA to help find our angle. All right, so for example 5, we're finding sine, cosine, and tangent for the triangle below. Here we know this side is negative 3, this side is 4, and then using the Pythagorean theorem, we know 3 squared plus 4 squared equals 25, which is going to be our third side squared, so that's going to be 5 squared. So 5 should be that third side there, just a simple 3, 4, 5 right triangle. Sine is going to be opposite over hypotenuse, which then should be the opposite side of theta is 4 over the hypotenuse, which is positive 5. So here, sine is going to be positive 4/5. Cosine here is going to be adjacent over hypotenuse. The adjacent side is going to be negative 3 in this case over the hypotenuse, which is 5. So that should be our answer for cosine. And then tangent is going to be opposite over adjacent, which our opposite side is positive 4. Our adjacent side is negative 3. So you could either write that or negative 4/3 there as our answer for tangent. All right, so for example 6 here, we are shown a circle on the left with angle measure theta radians. The terminal ray of the angle will intersect the circle at point R, and then point S also lies on the circle. We know the coordinates of R is negative x, and then negative y, and then the coordinates of S are positive x, and then negative y as well. So sometimes questions may not have exact numbers for coordinates, they may just have it in terms of x and y. Which of the following is true about cosine of theta? And so this is a common problem or issue that you'll see on these types of questions where there'll be 2 points, but it will only ask about cosine of one angle. And so the angle here, or like the point that we're going to work off of, whether it be R or S, is going to be looking at theta. And so we see theta as a shaded circle, and it goes all the way only to point R, not point S. So we can kind of ignore all of this. That's just kind of a red herring in this case. So if we take that and let's erase all that stuff. There we go. Now we want to find cosine of theta. And so cosine is, if we draw out our triangle, it should be negative x. Here is going to be our theta, negative y. And then our hypotenuse is going to be 8 in this case. And so you can always figure out your hypotenuse or radius with that point that's going to be shown there. And then cosine is just adjacent over hypotenuse. So the adjacent side is negative x in this case, and the hypotenuse is 8. So negative x over 8 should be A, should be our correct answer. And then looking at the explanation, Because it's a ratio of the horizontal displacement of r, that is true, because that is what this is, which is x. That's the horizontal displacement of r to the y-axis. And then the second part is saying the distance between the origin and r. That is their fancy way of saying the radius or hypotenuse there. So C or A should be our correct answer there. All right. Moving on to example number 7, the figure shows a circle with radius r centered. The coordinates of P is 4, 3, and then the radius of the circle is given to be 5 here. So find the coordinates of Q, R, and S. So here, these are just simple reflections. So if this is 4, and then this is 3, this is going to be -4, still +3. This would be -3 because they're going down. And so now we can fill in the coordinates. So for Q, it should be -4, +3. For point R, it should be -4, -3. And then for point S, it should be +4, and then -3 there. So those are 3 coordinates when they're reflected over the x-axis, y-axis, and origin. And now, using these points for examples 8, 9, and 10, we want to find the sine, cosine, and tangent of these different points. So take note how they're talking about different points here. And so for 8, we're doing sine of this angle right here, theta, where it intersects with P. So this is the triangle we're going to draw out. So for each one, I'm going to draw out a new triangle. So let's see here. So this one is going to look like this, where it's going to be 4, 3, and 5, and then this is our angle. So sine is opposite over hypotenuse. So this one should be opposite 3 over hypotenuse 5. So 3/5 there. Taking a look at the next one here, number 9, we're looking at point R this time. And so point R is talking about this whole angle right here. So this is the triangle we're going to want to extract. Drawing this triangle out, this is going to be theta. And then this would be -4 as that side, -3. So both of those would be negative, and then a +5 as our radius. Cosine is adjacent over hypotenuse. So this should be adjacent is -4 over +5, which is the hypotenuse or radius. And so that is our answer for number 9. Number 10, we're looking at point S. So that as an angle measure should be this whole thing, which means we're going to extract this triangle right there. Drawing out that triangle, we should have a right angle and then theta. This is going to be +4, -3, and then +5 as our radius. And we want tangent. So we want opposite over adjacent. Opposite here is -3. Adjacent is 4. So -3/4 should be our answer for example number 10 there. All right, example number 11. The figure shows a circle with radius 5 centered at the origin with an angle measure theta in standard position. So know how this goes to this line right here. Find the following as fractions: sine, cosine, and tangent. And so this is just a reflection. So this should be, instead of 3 and 4, it should be 3 and -4. And then our radius here is still going to be 5. So when we're working through this, this is the triangle we're going to want to extract, where this is our like theta, our right angle. We have +3, -4, and then +5. So sine being opposite over hypotenuse is going to be -4 over 5. Cosine is adjacent over hypotenuse for this triangle. So 3 over 5. Cosine will be positive in this case. And then tangent, opposite over adjacent. So -4 over 3 should be our answer for those 3 there. All right, now let's try 12 and 13. And so one thing important about these two is knowing that the tangent of an angle is going to be the slope of that line, right? Because if you think about just, let's go back to that 3, 4, 5 triangle, right? So let's just say we have this, right? tangent of theta is going to be opposite over adjacent, so 4 over 3. However, what is the slope of that line? If I asked you that, that is going to be rise, which is 4 over 3. And so tangent is basically the slope of that line. So if we didn't know what those two sides were, but I told you the slope of the line was 4/3, then that means tangent of theta should be 4/3. So let's use that as we solve 12 and 13. Let theta be an angle in standard position whose ray coincides with the line y equals 2x. So that's going to look like this in quadrant 1. And so here, find tangent of theta. So here I would just say tangent of theta equals, and then the slope of this line is just 2. So that's our tangent, 2. Let's try 13. This coincides with the line y equals negative 3x. So this is going to be our theta in quadrant 2. And so we want to basically take this triangle, find the slope of the line. So tangent theta equals negative 3 this time, because that is our slope of our line that we are given. So that's our answer to 12 and 13. So what we've done so far is we found sine, cosine, and tangent probably in all 4 quadrants. And so let's take a look and see if there's any patterns. And so there are patterns to where sine, cosine, and tangent respectively are positive or negative. And so if you take a look in the first quadrant, all 3 of these trig functions are going to be positive. In the second quadrant, and if you look at examples we've done before, only sine is positive. So here, only a sine, so S. In the first one, all, so A. In the third one, only tangent is positive, so T. And then in the fourth one, only cosine is positive, so C. So this is an acronym where it tells you which trig functions are positive in each quadrant. And the way I remember it is going from quadrant 1, 2, 3, and 4. All students take calculus. And so in the first quadrant, all trig functions are positive, only sine, only tangent, only cosine. And that's like a mnemonic device that a lot of students use to memorize where sine, cosine, and tangent are positive or negative. And so let's try example 14. The figure shows a circle with a radius of 5 and the points 3, 4. Which of the following statements are true? And so here, this angle is going to coincide in quadrant 4. So if we take a look at our trig mnemonic, all students take calculus, here in quadrant 4, only cosine is positive. Sure, we can find these things out if we wanted to by using 3 and then negative 4 and positive 5 and doing that, but we can actually save time just with this mnemonic device. So here, only cosine is positive, so 1 is true. Sine is negative, and tangent is also negative. So A should be our correct answer for example number 14. And finally, we're going to talk about coterminal angles. These are angles that are going to have the same location, but they're going to have maybe a different number of like full rotations. So for example, and this is not the example 15, this is just an example here. Let's say I have this angle. This is what 30 degrees would look like. However, let's say I wanted to have 390 degrees, which is 360 plus 30 to give us 390 degrees. That's going to appear with the same terminal ray or terminal side. This is going to be the same as if I had negative 330 degrees. And so just know they all will appear the same. Angles that do that are going to be coterminal. And so to figure out coterminal angles, all you need to do is add and subtract periods or revolutions of 360 degrees. So for example 15, find one positive and one negative angle that is coterminal with those 3. So for A, looking at this, we can use this graph as an example or help here. If we add a 360 degree rotation plus 30, we should get 390 degrees. That's a positive coterminal angle. And then for negative, we can subtract 360 to get negative 330 degrees. And that should be our answers for 15. Now doing 15b here, we're going to add 360 to get 405. degrees. And then we can subtract 360 as well to get negative 315 degrees. What C is going to look like 100 degrees, if we add 360, that should be 460 degrees. And then if we subtract 360, that would be negative 260 degrees. And so those should be our 6 answers for example number 15. And that's the end of day 1. All right, so for day 2, let's get right into it. Here's the bell ringer for today. So pause the video if you haven't done this yet, because I am about to go over the answers. So here what we want to do is, given the angle, we want to find a coterminal angle that is between 0 and 360. So for the first one, we have to add a revolution of 360 degrees because we want it to be a positive. This should be 340 degrees, and so that should be our answer. So remember, coterminal angles are angles that will appear or have the same terminal ray. So for example, there, or if you had an angle that included one rotation, or if you had one that was maybe negative. The next one, 395. Here we're going to subtract a rotation of 360 to get 35 degrees. So 35 degrees, and that's because we're just looking for one that's between 0 and 360. For 701, we're also going to subtract 360 as well, and so minus 360 degrees, and here we should get 341 degrees as our answer for that third one there. So today we're going to be learning about a new way to measure angles called radians. And so what exactly is 1 radian? A radian is an angle measure where basically this angle measure in radians is going to be a ratio of the length of this arc here to the length of the radius. So if you take that ratio, arc length over radius, you're going to get your angle measure in radians. And this is just another way to measure angles, like how you can use inches and centimeters to measure length. You can use degrees and radians to measure angles. And while we progress through this course, you will see that radians are used a lot more than degrees in problems. And so getting familiar with these is really important. Now, what exactly is 1 radian? What does 1 radian look like? Well, if we take a look, 1 radian would be when the arc length is going to be the same as the radius. Because when they're the same, they're going to be equal to each other, which would then produce the number 1. So what that looks like as a diagram is going to be something like this, where we have two radiuses r, we have this measure theta, and this means the arc length should be the same as the radius. So this is the arc length right here, this is the radius right there, and when they're the same length, that's going to be 1 radian. 1 radian in degrees is around 57.3 degrees. Obviously, it's a little bit, you can get a little bit more exact, but that's a rough estimation. And so that's what 1 radian looks like. Now let's take a look at example 1. Consider the angle theta created by a quarter circle of radius 4 above. We want to find this angle measure in radians. And then we were given that a circumference is 2 pi r, so that will be helpful for us as well. If we take a look at this, right, it's not hard to see that this is a right angle. So in degrees, it should be around 90 degrees, but we want to find it in radians. So remember, radians is going to be equal to arc length over radius. So we want to find both of these things. Obviously, the radius in this case is going to be 4. So that's not hard to find. Let's find the arc length. And so what we want to do is we want to find the arc length, we want to do 1/4, because it's only a quarter circle, times the circumference, which is 2 pi r. So here we would do 1/4 times 2 times pi times our radius, which is 4. These will kind of cancel out, and so we are just left with 2 pi. So the radius, or the radian angle measure, will be equal to 2 pi over our radius, 4. Simplifying this a little bit more, we should get pi over 2, and that is going to be our angle measure in radians. So it is important to know that pi over 2 radians equals 90 degrees in degrees. And so one thing that you will see about radian angle measures is not all the time, but a good majority of the time they will be written in terms of pi. So typically if you see something like, and we'll learn about this later this class, pi over 3 or 2 pi over 6, something like this, which is I guess the same, or 3 pi over 4, these are all going to be radian angle measures because they include some form of pi. And so let's learn how to convert radians to degrees. So as a reminder, for 360 degrees, that's a full circumference of a circle, right? This would be 360 degrees, which is one full revolution. So let's plug that into our radian angle measure. So radian is going to be arc length over radius. The arc length of a full circle is going to be 2 pi r, that's just the circumference, over the radius. The r's will cancel each other out, and we're just left with 2 pi radians. We don't even put radians at the end, because if it's given to us in terms of pi, we're going to assume it's radians. But now that we know that 360 degrees is equal to 2 pi radians, we can now convert degrees to radians using this conversion factor. So here, if we had degrees over 1, if we multiply this by 2 pi over 360 degrees, which this is, remember, these are both the same, so this is just multiplying it by 1. We're not changing it. We're not adding anything to it. This will give us our radian angle measure because the degree unit will essentially cancel out, and we will be left with a radian angle measure. Likewise, we can use this conversion, but we can simplify it. And so 2 pi over 360, remember, is just dividing both sides by 2, pi over 180. So this is going to be the conversion factor that I'm going to use, is pi over 180 degrees. Likewise, to convert from radians to degrees, if we went radians here, we can multiply this by, we're going to want our radian angle measure, pi, at the bottom, and then the equivalent, 180 at the top, and this will get us degrees. And so these two formulas are what we're going to use next to figure out some other important angle measure values there. So let's take a look. You won't need to memorize every single angle in radians, such as I'll never ask you what is like 57 degrees or like 62 degrees in radians. But you will need to commit a few angle measures from degrees to radians, kind of to memory, but also you can figure it out just by sketching out a quick graph of a circle. And so you'll need to memorize every multiple from 30 and 45 between 0 and 360 degrees. And so let's work on this. Example 2, convert each angle measure from one form to the other. So here we have degrees, we have radians, and then more degrees there. So we just got to convert it to the other. So let's do that now. And so for example 1, 45 degrees. If we do this times 180 degrees and then times pi, 45 goes into 180 exactly 4 times. So this will cancel out to just be 4. And so this should be pi over 4. So that should be our answer for A. So feel free to use a calculator with these. Let's try a few of these together, and then I will just give you the answers to the rest of these. So here, pi over 3. This should be pi over 3 times, and then here we want 180 over pi because we want the pi's to cancel out. And this should just be 60 degrees. So that's going to be our answer for B. C is pi. Pi is 180 degrees, but if we did the conversion formula, I would do multiplied by 180 over pi, and then this is just 180 degrees. D, 360 degrees is equal to, if we did the conversion formula, 2 pi over 360 or pi over 180. Those will cancel out, and we should just be left with 2 pi there. For E, 60 degrees, this is just going to be 60 over 1 times pi over 180. This will cancel out to be 3, so we should be left with pi over 3 there. Pi over 6, times 180 over pi. This will cancel out, and we are just left with 30 degrees. Pi over 4 times 180 over pi as well, cancel those out, 45 degrees. 720 degrees is just double 360, so it's going to be double the radian measure as well, so 4 pi there. 135, this would be one where I would probably give you a calculator for now until you memorize it, hopefully later on this class, times pi over 180. This should then be 3 pi over 4. Whoops. Simplifying that. So let me rewrite that. There we go. 3 pi over 4. And now I'm not going to spend too much time going over the rest of these. These are for you to kind of work out on your own. So try the rest now. Pause the video because I'm about to give you the answers. So for J, should be 240 degrees. K should be 330 degrees. And these are all ones that you will have memorized. 300 is 5 pi over 3. 225, 5 pi over 4. Let me circle my answers as well. 5 pi over 6, 150 degrees. Negative pi over 2, that's just going to be pi over 2, which we know is 90 degrees, but then with the negative sign, so just negative 90 degrees. Same thing with negative 45. If we look at A, 45 degrees is pi over 4, so this is just negative pi over 4. 0 is still 0 radians. That doesn't change. This should be negative 120 degrees. This would be 210 degrees. And then 1800, this is just going to be 10 pi. Right? So those should be all your answers to those 20 questions there. All right, so now we have the unit circle. The unit circle is basically just going to be a regular circle centered at the origin, but the key characteristic about this is the radius is going to be 1. Here, a radian measure is the same as the length of the arc formed by the angle, and this is important because our radian is going to typically be arc length over radius. But with the unit circle, 1 radian is going to be the arc length over the radius, which is 1, which is just your arc length. So your arc length here is going to be your radian angle measure when the radius is 1. And this is going to be super useful to help us find sine and cosine and different trig values. All right, so let's take a look at example 3. This circle below has markings of all the important angles that you'll need to know throughout this course. I gave you the first quadrant kind of for you. We're going to use these angles and a little bit of symmetry to fill in the remaining circle with the angle measures in radians. So here it's not as bad as it may seem. All you really need to know is 180 degrees is equal to pi radians. If you know that, and then you use a little bit of common sense, you should be good. So first, let's fill in that, right? This angle measure is going to just be pi. Now think of this. Pi, or 180 degrees, is one semicircle here, right? If we take a look at half of that, that is going to be 90 degrees. That's pi over 2. Now, that's 1/2 of a semicircle. So we're going to get pi over 2, pi, and then this is 1 1/2 of a semicircle. And so this should be 3 pi over 2. We're just going to add pi over 2 each time. Here, this would also be 0, or 2 pi would be the same there. So those should be our easy values to fill in. Now, if we take a look, let me erase these lines here. This is pi over 6. This is also 30 degrees. This is 45 degrees, and then 60 degrees. Think about it this way, right? This is 1/6 of a semicircle, because a semicircle is 180 degrees, and 30 degrees goes into that 6 times. So this is going to be one semicircle, pi, just cut into 6. And then if we keep on going, every time we add 30 degrees, we're going to add 1 over 6. So this should be 2 over 6. This would be 3 over 6. This should be 4 over 6. This one would be 5 over 6. We're going to skip the 45 degrees for now, and then this would be 6 over 6. But a lot of these can be simplified as well because 6 is a nice number that has a lot of numbers that go into it. So this is pi over 6. That's going to stay the same. 60 degrees here. 2 pi over 6 simplifies to pi over 3. 3 pi over 6 simplifies to pi over 2. 4 pi over 6 does simplify to 2 pi over 3, and that's going to be our answer there. 5 pi over 6 won't simplify, so we're just going to leave that as our answer there. 6 over 6 cancels out to pi, and then continuing this, you get 7 pi over 6. Here you would get 8 pi over 6. This is 9 pi over 6, 10 pi over 6, and then 11 pi over 6. Now let's simplify what we can. So here we have 8 pi over 3, or 8 pi over 6, and then 10 pi over 6. We can divide both sides by 2 to get 4 pi over 3, and then 5 pi over 3. There. Now let's do the 45-degree angle measurement, so every increment of 45 degrees. Here, this is 1/4 of a semicircle. So instead of it being pi, which is one full semicircle, it's going to be 1/4 of that, so pi over 4. Now, going in 45-degree increments, we're going to get 90 degrees. This is 2 pi over 4. This should be 3 pi over 4. This would also be 4 pi over 4. So simplifying this, 2 pi over 4 also simplifies to pi over 2. 3 pi over 4 doesn't simplify, so that should just be our answer there. And then 4 pi over 4 also simplifies to pi. So hopefully that makes sense. Let me now erase some of the unnecessary drawings and markings that we have here. And so that is going to be how we kind of fill in this unit circle without having to do that much math. Now filling out the rest of this, right? This is 4 pi over 4. This would be 5 pi over 4. That really can't be simplified. 6 pi over 4 is 3 pi over 2. And then this would be 7 pi over 4. So let me rewrite this. This one should be 5 pi over 4. Let me just write it a little bit neater. There we go. And so those are going to be all of your angle measurements in radians there filled out. So on your homework, you'll be asked to fill out this whole chart. This is how you are going to do it. So now let's get into our final thing for today, sine, cosine, and tangent on the unit circle. And so remember the unit circle is just when the radius is 1. And so when the radius is 1, that means our hypotenuse for any given triangle on that circle is also going to be 1. So while sine is typically y over r, it just now turns into y over 1, which is just y. Same thing with cosine. Cosine is x over r, which is x over 1, which is just x. So now sine and cosine are completely simplified when the radius is 1 into just our x and our y coordinates. If we take a look, tangent really doesn't change. Tangent's still y over x because we don't have any hypotenuse in there. Nothing really can be truly simplified with tangent. So that is just going to kind of stay the same. All right, so let's try example 4. One thing that is important to know is that for any unit circle, the coordinates of a point on the circle are going to be cosine, which is your x value, and sine, which is your y value. Now, in terms of how do I remember whether it's cosine first or is it sine first, I don't know. It's pretty easy, right? There's a few ways to do it. The way I learned in high school was the show CSI, Crime Scene Investigation, like CSI Miami. Here, you have cosine first and then sine, and then you just kind of ignore the I. It's just a mnemonic device. Another way is just alphabetically, right? Cosine comes first in the alphabet. So cosine is going to come first in your xy coordinate pair. So taking a look at example 4, we are given that the coordinates of point P are 1/2, comma 3 over, or root 3 over 2. Find sine, cosine, and tangent. So here, without even having to draw out a triangle and use SOHCAHTOA, we can just know, because the radius here is 1, we know that this is going to be our cosine of theta, and this is going to be our sine of theta as numbers. So here, sine of theta should just be root 3 over 2. And if we take a look, right, that is going to be true with if we did draw out SOHCAHTOA and did it the long way, right? This length would be 1/2, this would be √3/2, and then our radius would be 1. So if we did sine, for example, opposite over hypotenuse, that would be √3/2/1, which is just √3/2. Now, without doing that, right, because we just know it for a fact, we don't have to draw it out and use SOHCAHTOA. Cosine should just be our x-coordinate, so this should just be 1/2. And then tangent, remember, is going to be sine over cosine. So in this case, sine is going to be √3/2, all divided by 1/2. So here we're going to do √3/2 times the reciprocal, so 2/1, so keep, change, flip. Simplify this to just get √3 as your answer for C there. All right, so now taking a look at example 5, we now know the point R is the result after you take point P and reflect it over the y-axis, so that line of reflection there. Let A be the angle in standard position whose terminal ray intersects a circle at point R. So this is going to be A, or alpha there. Label point R on the unit circle above and find the following values. So here, this is going to be point R. Our coordinate should be -1/2 and then √3/2. And so let's find our values knowing that this is cosine, comma, sine. So sine should just be our y-coordinate here, which is √3/2. That's positive. Cosine should be negative, so -1/2. And then tangent is going to be sine over cosine, so √3/2 divided by -1/2, which is √3/2 times, and then the reciprocal, -2/1. Those cancel. Notice how that negative sign doesn't go away. So here, this would be -√3 as our answer for example 5. Taking a look at example 6, in the xy plane, two different angles A and B are in standard position and share a terminal ray. Which of the following gives possible values for A and B? So taking a look here, I would just sketch a very rough graph of every single one of these angles and see which two are going to appear the same graphically. So here, -π/2, that's going to be right there, and +π/2 is going to be up there. These two would not be the same because they would have different terminal rays. Taking a look at B, π/2, that looks good, and then -3π/2 would look like this. B should be our answer because these have the same terminal ray. If we take a look at, or that's C, B, -π/2, and then -3π/2, and then D, π/2, and then 3π/2. These both also have different terminal rays, so they are not going to be the same. And so that makes C the correct answer for example number 6. All right, so if you guys have any questions, please come into office hours, and I will see you guys later. Thanks.